Okay, in this video we're going to talk about properties of liquids and how to approximate those from data in the saturated tables. If you recall, we had the saturation diagram. Here's the volume, let's say. Volume does something like this as temperature goes up. We have VF over here and VG over here, just refreshing your memory, and then a constant temperature as you go from liquid to vapor, from 0% quality to 100% quality. Now, what happens, for instance, if you find you're over here in the liquid range? And that's what I want to talk about today. Liquid properties are a function of mostly temperature and maybe a little bitty function of pressure. So the overriding influence on the liquid is the temperature. Now you can get compressed liquid properties from tables and other means that we'll talk about later for some properties, but you have to often approximate it, because the liquid, if you have a moderately high pressure, then the compressed liquid tables just won't have the data in there, and you have to extrapolate it quite a bit. So rather than do that, what we're going to do is assume that if you know the temperature, given the temperature, the properties of liquids, for instance the volume, is approximately equal to the saturated liquid volume at that temperature, and we neglect the effect of pressure. So let's take an example. Suppose I told you the pressure of water was equal to, let's say 500 psi, and the temperature of the water was equal to 200 degrees Fahrenheit. Right off the bat, you know that's a liquid because water boils at 1 atmosphere at 212. You're not even hot enough at 200 degrees to boil at 1 atmosphere, much less 500 psi, 1 atmosphere being 14.7 psi. So the question is, what would you approximate to be the specific volume of that liquid water? So what we're going to do is we're going to assume that V is approximately equal to VF, which is equal to approximately 0.01663 feet cubed per pound mass. Feet cubed per pound mass. So if I told you the pressure was 500 and the temperature was 200 degrees Fahrenheit, you'd say the volume was approximately 0.01663 feet cubed per pound mass. I found that in the saturated water temperature table. Now for that same condition, what would be the internal energy of the water? So you go over and you'd say U is approximately equal to UF at 200 degrees Fahrenheit, and neglect the effect of pressure. And U would be equal to 200 degrees Fahrenheit would be equal to 168.1 BTUs per pound mass. Now, I recommend you follow along, get out your tables, and pause the video or whatever you need to do to check this and just confirm that. Now if you go to your compressed liquid tables at 500 psi, because we do have them at 500 psi, flip a few pages and you'll find compressed liquid water table, and you'll see that the actual volume of the water, including the effective pressure there, is 0.16607 feet cubed per pound mass, And we'll see that the internal energy of water is 167.7. So we're off by 0.4 BTUs per pound mass in the internal energy, and we're off by, gosh, we're way out there in the fourth significant figure for the volume. So often it's a very good approximation to do this. Now there's one case where you don't want to do this, and that's involving pumps, or at least one case, but particularly if you need a little more precision involving pumps when you're dealing with enthalpy, and we'll be dealing with enthalpy when we get to pumps, then you need to have a little more precise estimate of the enthalpy. So I'll next show you how to calculate the enthalpy, approximate it based on the volume and the pressure added to the internal energy. So let's go from, let's pull up a new slide and do that. Okay, what I have here are is the data for water for a temperature of 200 degrees. The yellow is taken from the saturated tables, and the orange is taken from the compressed liquid tables at a pressure of 500. You'll notice that the U of the water, the internal energy, is 168.1 here in the saturated case, and in the compressed liquid case we have U is equal to 167.7, so there's not a lot of difference. But you notice that there is a fair amount of difference going from HF to H. If we approximated H to be 169.24, we're missing it by, oh gosh, a little over 1 BTU per pound, and that may not be acceptable. In the case of calculating the work for a pump, that may be the most important part. So let me show you how I'd make that correction. Since we know that H is equal to U plus PV, then we can take H at a higher pressure and assume U is approximately the same between the two pressures, that the pressure doesn't have a lot of influence on the internal energy, but it obviously does have influence on the enthalpy because P is built right in there. So we take H at high P is equal to H at the low P plus, we'll take that delta PV, and assuming PV is constant because we have liquid, and a liquid is approximately incompressible, so assuming that the volume stays constant, we'd have plus V, constant V times P high minus P low. If we do that computation, we'll get H at 500 is equal to H at 11.5 psi. Here we had 11.5 psi was our saturated pressure, and that's where we had the H. So let's make that 168.13 plus V, which is 0.01663 times 500, P high 500 minus P low 11.5 roughly. Now this is in BTUs per pound, so we need to get this in BTUs per pound. We have feet cubed per pound times pound force per inch squared, so we need to multiply times 144 inches squared per pound per 700 per foot squared, and there are 778 approximately foot-pounds, let's say pound force foot per BTU. So it's a little messy, but you get the idea, and you need to stop, pause and do this calculation on your own. And when we make that correction, we come up with H equals 169.63, which is considerably closer than the 168.1. So we're getting in a little closer, and that's a better estimate, actually, of the enthalpy when we correct for the pressure. Because as you can see, H is equal to U plus PV, and P is built right in there. So we can't completely neglect pressure when we have enthalpy. It's a okay approximation, but it's better to make the correction, especially if you're dealing with a pump. So we've talked about so far that liquids are primarily a function of temperature, and we can usually use the saturated liquid value at a given temperature to approximate the property. But we need to make a correction if we're dealing with the enthalpy, and it's easy enough to do. Okay, finally, the example I want to do is, suppose I told you that the volume of water, sorry, I'm giving myself away, the volume of water is 0.01670 feet cubed per pound, and that the pressure was equal to 500 psi. And the question is, what is the internal energy? Okay, here you don't have the temperature. Here you have the volume and the pressure. Well, what you would do first is determine at that pressure whether or not it's a liquid, a vapor, or a mixture. So you go to your tables, and I'd go to the pressure tables at 500 psi, and I'd look up to see where the volume falls. Well, at 500 psi, VF is equal to 0.02044, and VG is equal to 0.675 or 0.676 approximately. Okay, so my volume here, 0.0167, falls to the left or lower than VF, so that tells you what? Keeping in mind this diagram, vapor, mixture, liquid. I'm over here on the liquid side of it, so this must be a liquid. So I've determined it's a liquid, but I don't have the temperature. So what you have to do is use this information and the fact that it's a liquid and approximate the temperature. We're going to say that V now is approximately equal to VF at some unknown temperature. So we have to find what that temperature is that gives me a volume of 0.0167. Well, I picked a value that's fairly easy to do. If you go follow in the tables you'll find that it's a lower temperature. It'd be a subcooled liquid. You go to a lower and lower temperature, and you follow the volumes until keep going down in temperature, down in pressure also, in the saturated tables until you get to a volume that's 0.0167. If you go to the temperature table, you'll find that occurs at right at T equals 210 degrees. So at 210 degrees Fahrenheit, we find that VF equals 0.0167. And that tells me that must be the temperature, because that's what's giving me that liquid volume at that point. Once you know the temperature, then you find the other properties. So I'll estimate the internal energy to be approximately U is approximately equal to UF, which at that point is 178.15. Seems a little tricky, and it is maybe, but that's the way you have to do it. Knowing that the temperature is the overriding influence on the liquid, you've got to find the temperature that gives you a volume of 0.01670. Had we estimated the internal energy from a pressure, UF at a pressure of 500, we'd have gotten a value for internal energy of 485. U equals 485, which is way wrong, because the temperature would be much higher. So the temperature that gives you 0.01670 is 210 degrees Fahrenheit, and that's what we use to find the rest of the properties, like for instance internal energy. So that concludes pretty much our a start into how to find properties of liquids. And just remember this: liquid properties are a function of mainly temperature and a little bitty function of pressure. So if you're in a pinch and you have to find a property quickly, then you can go to the saturated tables and find that property as a saturated liquid value.